Entonces, ahora tienen puntero y eso para pasar las diapositivas al mismo tiempo.
Ahora es el que están usando ellos.
Fantástico.
Just wait. 5 minutes for the people to start coming.
Always.
Yeah. Last minute. And we take also. Let's go on. Yeah, we should start 5 minutes after the time. 11, 5. Waiting for them to come. You have a video, you have no. So, look, picture just drinking latte. It was really good. Good picture.
I was excited, so I didn't sleep. So
Last night. Yeah. That's normal.
this morning, I was a little sleepy, so I drink some tea.
Yeah. That's normal. The night before your presentation, you just start thinking of it.
No. I just think of Tango.
Django, good. You like it? You enjoy it?
I really enjoy it because when I was in the university, I said, hello, and I danced. My partner. She's my partner. My dancing partner. 20 years ago. Okay, well, and then you return back to the and then when she was on the student, he go to the party and
I think you forgot to answer that time.
nowadays I play
Después que te lo arreglen otra cosa.
Sí, igual lo hice. Sí, casi no lo encuentro. Igual
bueno,
aparte va a salir bonita.
entonces ahí pueden dar la
Ya estoy. Ya.
What's happened in the conversation on mic, so yeah, and if you have, if you have fun,
Voy a cambiar domicilio de DNI para sacar buenísimo.
Empezamos. Bueno, buenos días de nuevo. Hoy es el turno de Mingxia, Wang, está with Mingxia. Ella es un contributor de Spanish. Ella es profesora de ciencia en ingeniería ambiental en la misma universidad que Conferencia, en la misma facultad de recursos naturales y medio ambiente. Es profesora, tiene varios estudiantes de doctorado, ellos tienen muchos estudiantes de maestría también, porque primero hacen un par de años de maestría y después de la maestría hacen su doctorado, tienen muchos estudiantes también de maestría, y ella se especializa en temas ambientales, ingeniería ambiental principalmente, tiene 60 trabajos publicados, y hizo la tesis también en la misma universidad. Es especialista más que nada en procesos de absorción de metales pesados en componentes del suelo, como cadmio, arsénico, sustancias, o sea, cuando ocurre relacionadas con lo que hacemos nosotros, sintetizan muy bien los óxidos, muy bien las partículas, así que seguramente nos va a mostrar unas muy lindas fotos. Y bueno, además de ser muy buena científica, muy buena amiga, es excelente bailarina de tango. It's a thing. Good man and good scientist, you are excellent tango dancer. Nos pasó el trabajo a todos la noche. You were the best last night. So, floor is yours.
Okay. Thanks, Professor and I'm Mingxia Wang, come from the University, China. Today, I will give the talk. Is phase dependent surface reactivity and the lead absorption characteristics of iron oxides, CDN modeling. And the story I will tell today maybe in two parts. One is the surface reactivity of different iron oxides. And these three oxides is normal one in soil, and the different soil color equals different oxides. This red color means naming is habitat, and yellow color is sulfite, and the brown carbohydrate. The other is the unity parameter of CD modeling. Called CD modeling is a kind of surface compensation model, and is a useful tool to describe the surface properties of oxides, including iron oxides. Firstly, I will give some background. We know iron, the content of iron in crust is ranking fourth, only second to oxygen, silicon, and aluminum. And also iron oxides, nano type of oxides, are distributed throughout the atmosphere, waters, in oceans, surface water, also some groundwater and soils, and in most of the living organisms. Also, they are widely used in some industries such as steel, chemistry, and pigments. Also from Earth to Mars. This is an example of the ion cycle of nano mineralogy and nano geoscience research. And because of a discovery that their chemical properties vary as the function of the particle size. And this variation mainly due to maybe most partially due to their surface atomic arrangement of surface atomic structure, and as well as their crystal shape or their surface topography. That's from the nanoparticle size to this large size. Iron oxides play a very important role to influence the geochemical reaction and mechanics of hydrosphere, biosphere, etc. So this we can see it's very present widely in nature. And for their wide existence in soil, iron oxides generally exist as a curtain. This is a curtain or fine particle in interface of soil, aggregates or soil particles. If there are some heavy metals in soil, they will absorb heavy metals and will set the heavy metals specification and further set their availability. I just mentioned silicon model is a useful tool to describe the surface reality for the heavy metals of oxides. And we all know lead is a highly toxic element, and it has a strong absorption affinity towards these soil particles. And we all know the toxicity of the viability of lead heavy metals are not related to total amount, and more related to their speciation in nature or in soil. So it's very important for us to figure out the chemical specification of these heavy metals in soil. But we know these iron oxides, they rarely exist in nature as pure phase. They often contain some elements like aluminum as isomorphous substitution. Aluminum is also very popular in crust in soil. And we know aluminum substitution can change the oxides, their crystallography, and mineral and chemical properties. So we want to know what's the impact of the surface properties on aluminum substitution on the iron oxides. And two, how does the sedimentary modeling clarify the lead complexation on aluminum iron oxides. Secondly, I will introduce the materials and methods very briefly. First, we use a homogeneous precipitation method to synthesize pure or illuminated substituted ferrohydride, bauxite, and hematite, and characterize them by XID, SPAs, SEM, etc. And then we got some acid-base titration and a late absorption data, and then we use a signal model to predict, to clarify the surface properties of those iron oxides. The result first for ferrohydride, and we synthesize 2 ferrohydride, and the ferrohydride is amorphous ions, and we find that the substitution of aluminum isomorphous to ferrohydride lead little or slight increase in the proportion of this sort of water, and some slight decrease or unchanged so much for hydroxyl, and for the SSA of ferrohydride, they just decrease slightly. As for the bauxite and the hematite, we can see from the XID section, and they change just unchanged. They almost the same. And for the SPAs, for the bauxite, the hydrogen amount really unchanged, and also the SSA for bauxite decreased, tend to decrease, not so much. But for hematite, the texture content increase with the increase of the aluminum substitution, and SSA for hematite doesn't change so much. Then on changing a little. And for the surface charge, we can see the surface, the charge density curve, and compare for the pure ferrohydride. The illuminated system, the surface charge only increase in a slight increase, and the PCC of all samples changed significantly. So for from the SEM and EDS image, we found that the shape and the size for the ferrohydride was less affected by the aluminum substitution, and also the absorption complexities of ferrohydride was affected not so much. They are all identical combination. But for the bauxite and the hematite, it is different. We can see the pure bauxite and the pure hematite. The surface charge of pure bauxite is a little higher than that of hematite. But for the aluminum substitution system, both side, the surface charge of both sides lower than that of hematite. This is a very interesting result, because we know normally the gold site is more active than hand-tied. Why? For the aluminum system, the tendency is reverse. We don't know why. And for the absorption of link, is the same the same result. For the gold side and the hand-tied is the different. The change of the link absorption is different. For the gold side, with the increase of aluminum substitution, the capacity decrease. But for the hand-tied, increase. We don't know why. And sorry. The capacity amount for hand-tied is larger than the gold-tied. So we want to know why for the reverse result. From the TM image, we found the substitution just they don't change the morphology of aluminum substituted gold site, just change the length to width ratio. This is the image, and this from the revealed refinement result. We found this one pure gold site. Their 110 ratio fraction is about 91, and 102 is 9. This is the city milk modeling results. We can see for the pure gold site it fits well, but for the aluminum substitute to the gold site, it's not so well. From this result, we think this is because the parameter is the classical suction parameter for the city milk the major crystal plane is 110 and 021, and the fraction is 19 and 10. It's similar to this one. So we just use the realization form we calculated and found the fitting result as well. So we use this late absorption result and found that the main surface complexes are identical ones, and G1, G10, G15 is also the same. But for the hematite, we can also see the city milk model can match well only for the H0, means for the pure phase, and for the H5, H2 is not so good, because aluminum substitution on its morphology, we can see H0 is like this one, but H10 is this shape, and from the hydro to this shape. So it is different. But it's also very interesting. Why? Because for the hematite, this shape, the major crystal plane is 001, and normal 001 is non-active. That means it should be no no charge, most of this charge lower, but is higher than this one. So we want to know why is larger than this one. Is the 001 is active? We want to find out. So we synthesize two different morphology hand types. They are hand types, and one is nano plate, and one is nano. And all these hand types were well defined shaped. So we use this to find the result. This picture it shows the surface atomic arrangement of hand types. And for the different plate, this is 110 plate. Every plate they have each plate has a constant surface size contribution, and 110 they have contain three can of surface size, and 012 they also. But for 001 they only doubling coordinate size. This is neutral. That means non-active. And these three phases are equivalent physics. And we also find the surface density of HNP and HNC, this nanocube, this nanoplate. We find that the surface charge of nanocube is slightly higher than that of nanoplate, and this is the significant parameters. And we found that the solid lines fit result. They are fit well, and the 1, 2 phases, they have the different log K value is that 110. And they have the different phase distribution, and this is the thermal capacitance. And we also got the good fit result with the rate absorption of HNP and HNC. And the HNP, because 001 is non-active, so they only has is 012 on HNP, and HNC they has two major planes, 012 or 110. This is the compensation species ratio. And then we also find that HNC, the 0 1 phases, their absorption rate amount. We found that 012 phases of hand type show the larger rate uptake than this one, than 110, and more greater pH dependence than 110. And we also find some experimental data from the literatures, and we use the parameter from our work, HPC and HMT and HMC. We found that this the sketch symbol and the experimental data from the literatures, and this solid line is our fit result, we can see that match very well. And this means our findings, that means our findings predict, can be used to predict the habitat, and also prove that the 001 for the habitat is not active. So we return to the beginning. Why? What the real reason for the dramatic increase of lead absorption or proton absorption of luminous substitution abstract? This is the picture for the pure one and the aluminum substituted ones. We find because the substitution, the 001, they produce some vacancy, and this vacancy in many studies, they also tell this vacancy is very active. So this is the main reason why the aluminum substitution oxides are higher capacity than the pure one. In short, we compare the three different oxides for ferrihydrite, goethite, and hematite. For the aluminum substitution, for ferrihydrite and goethite, they all decrease with the increase of substitution. But for the hematite, it increase with the increase of substitution, because they change not so much, but at least produce many vacancies. And this is the significant parameters for proton absorption. We find that for these three kinds of oxides, the total density don't change much for the aluminum system, but this for the habitat changes so much, not for the other two. But for the low K value, they are the same type of the surface size. They have the similar, and captors will increase for this one, and for this two, and decrease for this one. And we also have had the same result about lead absorption parameters. The aluminum substitution for R size is to the decrease, a little more decrease for this one. But the same there, the low K value, the same lead complexes on different ions is relatively similar. So these results give us a hint that a unity set of these three kinds of oxides may be possible. Actually, some studies have derived some generic model parameter for these oxides. For example, for both sites, they establish a relation about SSA and some other parameters. And for ferrihydrite, someone fixed the locale and the mass density. But for hematite, because the diverse shape, so they have no generic parameters. But we want to try. Because why? To our knowledge, despite they have diverse shape types contribution, but the unit, they are similar of the hydrogen ion. So they have similar ion to zero bond and similar distance and etc. And then also they have the same surface side for this one and this one. So it may be we can find a unit set. So we collect many experiment data, find 6 sets of useful experimental from the literature, and we consider their surface charge, consider their protein binding, acid-base titration data, and some dependent condition, and some other like the particle size, crystal morphology, and almost aging time. And we found that the proton of fluidity constant and the stern layer capacities and the SSA for ferrohydride. These are the sensitive parameters for the cylindrical modeling, and these two are insensitive parameters. And the stern capacity have a very simple correlation with the SSA for both side time and ferrite. It's okay. It's also okay. And this is our cylindrical parameter unit set, and we give a good modeling for the parent data and our predictor data. You can see it's matched very well. So we find satisfied results, and our results have been published in water research recently. So come to the conclusion. We can conclude for both sides the surface charge increase mainly due to the decrease of 102 to 110 crystal plane ratio, while for habitat due to the large productivity of vacancies. For the lead absorption capacity, increase with the increase of return for habitat, while decrease for these two. For the lead species distribution, relies strongly on habitat basis, and large lead uptake and greater cage dependence on 012 visit more than 110 visit. And we also proposed a set of generic model parameters for iron oxides. And this route we thank our group member of soil, chemistry, and the environment at Atlantic University, and we also thank the financial support of the National Natural Science Foundation of China. And thanks for your attention.
Thank you. Yeah, thank you. Yeah, very nice presentation. A really large amount of data you have presented to us, and it's really nice. So we have some questions.
But my question is, you work at different pH, a very wide range of pH.
Yeah.
What happens with the lead speciation? Because you have always you have a lead with 2+.
Yeah.
Yeah, in all the range, in all the pH.
And the latest species shown here just the significant model calculation. Surface low evidence of the spectral.
Okay.
Yeah, no, but in solution,
Yes,
in solution, you consider all the species.
Yeah,
in solution.
in the solution, not in.
Yeah, not,
Yeah, but just the calculation.
yeah, of course.
Yes.
That you have the pKa or just
Yeah.
to know the speciation in solution of all the species.
Yes.
Some
Easy,
sort of
okay.
timing from some. No, but the question is also from the experimental part. I think that this is the basis. It's not easy when you change the pH. In the experimental part,
Yeah.
if you want a different pH, probably you have problems with the linear solution.
Yeah, but you consider all the species that they could be in solution. Yeah, to check the equilibrium constant from the literature. That's not you have lead 2 plus, lead 08 plus, and lead all the species, all the possibilities. Yeah.
No, it's all the calculated, and for some special data, we just prove for the some detail.
Because I don't know the significance.
Otra pregunta. I have questions. How many species you consider at the surface? They were all the same for four species.
Yes.
Four species. And can you see them? Can you detect them by some spectroscopy? Please compute them.
Because for the gold side, the lead is very difficult because the signal of the iron will affect the signal of the lead.
We want to
We do many results, but the result is not very good.
Okay. You did simple from experiment.
we did a little, but calculated.
Yeah. Well, I don't remember your distribution at the surface, but they were all important, or they were just one or two? They were the most important ones at the surface, and the other ones.
At a different concentration, the species is different.
It changes with concentration of the concentration.
Yeah,
And also with pH.
pH and concentration.
We all have that.
Yeah. Otra pregunta. How you prepare your nice platelet particles? How you do that?
I know you are interested with this. That's the
How was the synthesis made?
HMP, we use the hydrothermal method. And for HMP,
The sodium acetate,
yeah, and
iron chloride.
just with what? Ethanol with
What's that? That's
0.7.
alcohol.
Alcohol,
Ethanol.
Ethanol.
I need ethanol and water.
It's, yeah, 0.7 for HMP and 2.5 for HMC.
So I did change the proportion of ethanol in your synthesis solution. You can use platelet or those.
Yeah, this is the difference only for the other one is the same. All the same.
Listo. Another question. Okay, well, thank you again. Y ahora es el turno de